So if we want to use activity coefficients and activities to account for non-ideal behavior, we need to be able to measure them. So for the solvent, that's pretty straightforward. Because the solvent activity is defined as this ratio of the vapor pressure of the solution divided by the vapor pressure of the pure substance, this is something you can just measure, right? If you measure P1 as a function of mole fraction for our solvent, as you get more concentrated solutions, you can see this vapor pressure decrease, and you will be able to, you can just directly calculate this, because then this value of P1 star at the given temperature that you're at, and you can calculate the activity. For the solutes, it's a little bit more complicated. And just as a reminder, because often what we will find is activity coefficients instead of activities. I forgot to put this in the last video. The activity coefficients are just the ratios of activities to concentrations. So for example, for gamma for the molarity version 2C, we have the activity divided by the concentration of component 2, which is our solute. And you have similar expressions for, if you express in terms of mole fraction, you get the activity divided by the mole fraction. If you express it in terms of molality, you get the activity, the molality version divided by the molality. Right, so anyway, often what we find are these ratios instead of directly the activities, but once we have the ratios, then we can find the activity. So if we want to do this for the solute, as a reminder, the activity is equal to P2. Instead of over P2 star, it's over KH2. And we need to be able to measure what's the vapor pressure of our solute in the solution, which there's, number one, not very much of it in the solution. And number two, it is usually a solid, so it doesn't have a very high vapor pressure in the first place. So often you can't, not often, usually you can't measure this directly. With the solvent, it's easier. You can measure that pressure directly, but with the solute, you can't. So we need a different way to get at finding activities and activity coefficients for the solute. And this is going to be somewhat similar to what we looked at with fugacities, right? We need a way to relate our ideal and non-ideal, and then come up with an equation that lets us, find from experimental data how we can do this. Now, in this case, we have an advantage in that because we can measure the solvent activity coefficient, there is a relationship between those two, right? There's a relationship between the Gibbs-Duhem equation tells us that there's a relationship between our chemical potentials for our two different things in our system. And if we use the equations that the chemical potential in terms of the activity, right? We have just as a reminder, we have something that looks like this: mu1 equals mu1 star plus RT log of the activity, either 1 or 2. And that means that if we take d mu1, that is just going to, right, the first term is a constant, so you're just going to have a term that looks like d log A1. And so we can write the Gibbs-Duhem equation specifically for this sort of solid liquid solution as N1 d natural log of A1 plus N2 d natural log of A2 equals 0. And now we have something that directly relates activities for the solvent and activities for the solute. So if we can find the activity for the solvent, we can then determine the activity for the solute. Okay, so let's just talk about how we can, let's go through the math of how we can do this. All right, so if we know natural log of A1, we can say for the solvent, if we're under ideal conditions, this is equal to x1, right? That's sort of how we defined activities, is that under ideal conditions, the activity should turn into the mole fraction for the solvent. So this is if the solution is sufficiently dilute and it behaves according to Raoult's law. Okay, and that by definition is the natural log of 1 minus x2. That's just definitions of mole fractions. And then we can make a mathematical approximation here that this is about equal to negative x2 if x2 is very small. So this is a approximation that you can make with logarithms. Okay, now we'd like to express x2 in not mole fraction, in some other unit. And so we can do this by using the molecular weight of water, and what's the approximate molality of like pure water. Anyway, the details in your textbook, I'll just show you the equation. We can say that x2, and this is an approximate here, x2 is approximately equal to the molality divided by 55.506 moles per kilogram. And this comes from the molecular weight of water. So this is specific to water. Okay, so through all these steps, right, if we go from log A1 to this, we can say that natural log of A1 is about equal to the molality divided by, and a negative sign here, divided by 55.506 moles per kilogram. Okay, so that's what we expect for ideal behavior. And so if we want to measure the deviation from this ideal behavior, that will tell us, that'll let us calculate activity. So in the next video, we'll follow through the next steps of this to figure out how we can find the activity and activity coefficients for our solute.